Okay, hopefully this does work. Sorry for the delay, everyone. I'll try and go even faster. So, okay, first off, to make your own airfoil, you can use a tool called airfoiltools.com. You can literally, if I go to like, you get like your own freaking like 4-digit generator that like, basically a knockup profile, as we were talking about. It's an airfoil made from the NASA. This is NASA's original name, I'm pretty sure. And then basically the naming convention is max camber is the first number, then max camber position is the second number. You can see it's just divided by 10. And then the thickness is the last 2 digits. So I'm pretty sure the 4412 is what we use on our front wing. We can change that to 200. We can close the trailing edge. So it's a nice sharp trailing edge. And then, like, you know, you can play with this. So, like, you know, you can make this like 10, and it makes it look super weird. So yeah, stuff like that. So let's do the 44. So basically, if you want to import this into SolidWorks, you copy this. And I mean, like, there's another way for you to do it. You can like send it to the plotter, and you can download the CSV file or whatever, but I'm not going to do that right now. So then you just open up Excel. I don't know how to do this in Sheets. If you want to do it in Sheets, I guess you're going to have to figure it out on your own. Then do data, text to columns. Then you want to separate it by space. So it's going to do that. You then want to basically, and I'll explain what these all are. So basically, like, this is your x coordinate, this is your y coordinate, and then you have to add your z coordinate. So you can literally just do that. And I know there's a way to make this go faster. You just, but whatever, who cares? Okay, so yeah, so now you have your x, y, z. This, when you import it into, when it outputs it from Airfoil tools, this is in units of meter. When I'm going to import this into my SolidWorks file, it's going to import it as millimeters. So what you're going to actually want to do is want to do that times 1,000. Basically do that, copy that, you're going to go back up to the top, and you're going to paste it just as a number, just as the values. Oh my goodness. My computer's just dead right now. Holy shit. Okay. Then you want to delete this. So now it's literally just your XYZ coordinates in units of millimeters. Then you're going to do File, Save As. I'm going to put it inside of my Downloads folder. And I'm going to save it as, where is it? Text tab delimited. Right here. And I'm just going to call it Airfoil. Okay. I'm going to close it. And I'm going to create a new part. If you're doing something for Formula Motorsport or Formula Electric, I am requiring you that you select the correct template. If you don't know how to, if you don't know how to do that, I'm sure there's instructions online, or not online, on the Z drive, or you could ask me. So now you're going to want to do File, Insert, Curve through XYZ points, and then let me bring this over. You're going to want to browse. It's already in the Downloads folder. Change it to Text Files, Airfoil, and okay. And boom, now you have an airfoil. So then what you're going to want to do is you're going to want to click on, I guess, this plane because it's lying on that plane. And then you're going to want to just convert it so that, like, you basically leave the curve on its own. You don't touch it. You just convert it into a new sketch, and then you use this conversion for your whatever you want to do. And then if you want to, like, modify it, you can always delete this like relation. So then you can like, scale it with like the move or copy or whatever you want to rotate it, whatever you want to do. So I guess, yeah, let's go ahead and do that. This is going to be a nice little interesting question for you guys. So let's go over to the Airfoil tools. And Airfoil database. There should be the 4412 in here. If not, we can do the 2412. Oh, no, there it is. So this is the 4412 as we did. And so within this tool, you can also plot something called the polars. So here you have like coefficient of lift versus coefficient of drag, coefficient of lift versus alpha, coefficient of lift, like the efficiency over alpha, et cetera, et cetera. So let's say that from our, why is it not? There you go. Okay, so let's just extrude this 1 meter. So as I said, I'm pretty sure this is 1 meter chord, and we're going to measure it too. This is 1 meter chord. Who here remembers the definition of the Reynolds number?
Viscous over the frictional.
Viscous over frictional?
It's a function of the like viscous and frictional to give you like how well it's gonna stay in there.
Yeah, you have the viscous right, but it's not frictional. It's inertial over viscous. So, yeah. So, okay. Basically, you see the Reynolds number right here, and we have a Reynolds number, or the length is basically 1 meter. Let's say we're going to simulate this as, actually, we can just do like, you can literally just take the Reynolds number. Ryan Reynolds, yes, this one. So like kinematic viscosity, we have a chord length of 1. We're going to do velocity of that. I'm pretty sure this is the value for air. So if we simulate this at 10 meters per second, we're going to have a Reynolds number of 700 and some odd thousand, which means that we don't care about the 200, the 100, or that. We can update the plots, which now we have the two curves we care about. So, does somebody want to tell me what angle of attack they want to simulate the airfoil at? On Discord, anyone? Does anybody want to? It doesn't even have to be a right number. It just has to be a number. What angle of attack do you guys want to simulate this airfoil at? 7? Okay, we're doing 7. So that's going to land about right here. If you wanted the theoretical max downforce, this is telling us like maybe 14 would be the optimal. But you're playing with fire if you do that. So okay, we're going to do 7. So we're going to go back. And you can either rotate it as a solid body, or you can also rotate it within the sketch. I'm going to choose to do it in the sketch. So I'm just going to rotate that, center of rotation. It's going to be the trailing edge there. And yeah, you want to unselect keep relation. That one always messes me up. So -7. So boom. Okay, now here's another little fun thing. If you ever want to get like the plan form area of something or the frontal area of something in SolidWorks, you can always do something called the silhouette. And that's basically going to get you this like silhouette of it. And then you can measure that, or you can like to get your like top area, you can do the same thing for your frontal area as well. But yeah, so, all right, so we have our wing. That's one way of doing it. Let me go ahead and hide this. The second way of CADing in Airfoil, a little bit more custom. I'm not expecting you guys to do this. I'm just kind of showing you just for your curiosity, if you want to call it that. Basically, you create kind of like your trailing edge is going to be right here, and this is going to be your leading edge. And then right here, where I'm sketching this like little, I don't know what you want to call this, basically the camber. This is the where left the max camber is going to be, so I'm going to make those equal. It's kind of annoying me that I'm not able to see the sketch relations. And to be honest, I always forget if you want to make it perpendicular to this one or this one. I guess it doesn't fully matter. It's fine, I'll keep it like that. So next what you're going to want to do is define your trailing edge. Like that, and we know the trailing edge is going to be perpendicular. So we're going to make this like maybe, like, I don't know, 3 mm. And then what you're going to want to do after that is define these two lines, and these are going to be your trailing edge tangencies. Those are going to be parallel. And for sake of simplicity, we're going to make these parallel, but theoretically you don't have to make them parallel. You probably might actually want to not have these two be parallel. You might want to have them like at a certain inset angle. So that shit. Driving and oh shit. So okay. Make that like 85. Make this 85. Yeah, sure you go. And then let's see. Okay. If you ever see something that isn't constrained, you can always just move it and or like move whatever's blue and see how it moves. And try and figure out what's going on. Okay, so now I'm going to define my come on. Oh, it's just a little weird angle. Okay, so that's my horizontal line. I'm going to make these. Sometimes I really hate SolidWorks. Linear. So next thing I'm going to define is my chord line. So make this 7. We're going to make this 1 meter. And then we said for 4412, this should be 600 from the trailing edge. And then this is your calculator. Here's your calculator. What is 6%? Oh wait, I can just do 6% of 1,000. That's 60, right? 60 mm. Okay. And then after that, the last thing remaining is that this distance from here to here should be 4%, so that should be 4. Okay, so now you basically have your like governing sketch. So now you're going to use a spline. The spline's a very powerful tool, but it is a pain in the ass to work with, especially if you don't know what you're doing. But basically, you click on it and you can like drag these little like arrows. You can already tell it's like kind of being a pain. So basically, you're just gonna want to like take these arrows. And there's two things you can control with them. Like there's the magnitude and the vector, or like the direction. So like I made that tangent with that. Sometimes I define another like sketch line right here and define that as tangent. You don't have to. You can define this as perpendicular. And you can like change the magnitude of it. And you see it's like kind of looking airfoil-y, just a bit. And then you can do the same thing for here. I do know this is how Formula 1 teams do their airfoils, because they're obviously very specialized, and they obviously have the manpower to do it. And knowledge. Knowledge is the big one. Shit. Like, see, like, this is why sometimes splines are just a big pain in the ass. Okay. So, like, you know, it's like maybe not the world's, you know, best airfoil. Like, no one's writing a review about it. But, you know, it's like halfway decent. It's actually looking, yeah, it's looking halfway decent. And then all I gotta do is zoom in. I technically didn't need to make this construction line. Could have made that. It's filled in, which means it's fully enclosed. And boom, I can extrude it. And we have an airfoil. So yeah, that's how you make your own custom airfoil. And then if you want to be like super overpowered, you can technically make these equations. And then you can just like change the equation, like, you know, you could do like equal whatever crap, and then like relate them to each other. So like for this is 1,000, so I think I could technically make like this one equal to like 0.6 of this, some shit like that. But I honestly kind of forget how to make relations inside of SolidWorks, so we're not gonna go with that. Okay, anyways, let's go ahead and hide this custom one that I made. Show the actually like official one here. So basically, to export this, what you're going to want to do is you're going to want to highlight the solid body you want to use, and you want to save it as, I do step, as step function. Fuck, where do I want to put this? Training, arrow. We'll call this winter 23. Training. Okay, and then you're going to want to save it as a step 214. I do know, I have heard some people like to use parasolids, and I guess that's fine. I prefer step. I don't know why. Don't ask me why. Just what I do. And then after that, you're going to want to do selected bodies. That's why we selected this. So like, if you're working on I don't know, some part file that has the rear wing and the chassis inside of it because you wanted to design your front wing while seeing your chassis so that you wouldn't design them to be like interfering, which is a good practice, but you don't want to export the chassis. You just select the front wing solid, then you do that. So it's going to export it. So I exported it to the Z drive. Training, aero. By the way, if you want to see the recordings from the summer term, these are them. I basically just reused the exact same slides that I did for last week. Okay, so we're just going to go ahead, copy that. And then we're going to go to, I guess I'll put it in my downloads. Sure. Okay. Okay, so now we're basically just going to create a simulation from scratch. So there's many ways you can start this, I guess. I'm just going to start off by just importing it, just because why not? I don't want to create a scene. All these other things you can modify once you get good enough. And basically you just use this so that like you control the quality of the import, basically. But for now, don't worry about it. I've only really had to worry about it in industry. Anything that we do here, it's pretty simple enough where we don't really care about it. Okay, next I guess we'll create the actual simulation physics. So this is like the governing mathematical model that will govern our simulation. So we want it to be three-dimensional. It's gonna be a gas. It's automatically gonna select air, by the way. We'll do segregated for now. We'll do constant density, incompressible. Why? Because we're less than 0.3 Mach, as I talked about last week. It's going to be steady simulation, turbulent, and it's automatically going to select Reynolds average, Navier-Stokes, and then we're going to do the K omega model, and it's going to automatically select the SST model. And then all the other stuff is optional, so we don't really need to select it. Next, we're going to create a geometry scene. So boom, we have our wing, but we don't have a domain. I could have created it in SolidWorks, and all you have to do is recreate the same. Actually, there is a somewhat important step if I'm gonna want to show you guys. Okay, let's go ahead and do a sketch on this one. We will just do a box. Shit. Do that. I don't know. We'll do like 3.5 meters. And we'll do like 4 meters. Doesn't need to be that big. Okay, exit. One mistake I made about this is it's probably better for me to just do it mid-lane. There you go. And I'm not going to merge it, and I just want to keep the two bodies, domain and wing, separate. Same thing. So that little icon there is the import geometry button, basically. Okay, so now we have, I'm going to rename this for my sanity. Okay, so now you're going to want to open up the surfaces within the domain, and you're going to want to do split by patch. You're going to want to select this, and you're going to want to name it inlet, create, this one you're going to name outlet, create, and you can close it. And then we'll just rename this one symmetry, or just sim for symmetry. Okay, next up we're going to have to take our actual domain and subtract out the wing. How am I doing on time? 30 minutes, not bad. I'm going to try and get you guys out of here as soon as possible. Boolean, subtract, then I'm going to select everything that is involved in the operation. Then I'm going to select what I want to keep. I want to keep the domain, and just select those two, then boom, and then I'm just going to want to go ahead and see that. So latest volume, select the subtract, and then I can make it transparent with that button there. So I can see that I've subtracted out the wing from the domain, and it's offset for some stupid reason. Oh, that's okay. Whatever, who cares? Okay, then I'm going to want to create a region. So this is basically where it's going to take in the physics and the mesh, and all the parts that you assign to it, and it's going to link them all together. I guess that's a way you can think about it. So basically, you have to assign it a part. So we're going to assign it the subtract. It's already assigned itself to physics 1 that we made. And then you can see that it has this as the boundary conditions. So we already know that we're going to need 4 for the inlet, symmetry, outlet, and the wing. Let me see if I can undo that. You should be able to just do F2, yes. Wall. Or actually, sorry. Sim. Then inlet. Then outlet. Obviously, you're going to want to change the symmetry to symmetry plane. Inlet to velocity inlet. Outlet to pressure outlet. Pressure outlet is automatically going to set it to 0. That's fine. You don't really need to change that. Velocity, we said 10. Wing, it's already a wall basically. That's fine. Symmetry, there's nothing you can change about it. Don't want to. Last thing to do is create the mesh. So we're going to do an automated mesh. So we're going to do surface remesher, automatic surface repair. We're going to do a trimmer cell, because it's the most efficient for memory and it's faster. Because, yeah, and then just do OK. Select the subtract, do OK. Okay, sweet. Let's go ahead and execute that. And let's create a mesh displayer. And let's hide everything except the wing. Where's the wing? The fuck? Did the meshing just get rid of it? Oh, no. Okay. I was hoping I could. Let me see. I mean, yeah. I know. I was gonna try and see if I could ask you guys questions to help me make a mesh, get your guys' brains flowing. Let me see if that. Wait, was it actually? Ooh, good catch. Good. See, juices are flowing. Fuck. I don't know why the wing isn't showing. Oh, wait, you know why? You know why? Because I didn't assign it. Because I didn't I didn't assign any of them. I'm so stupid. Symmetry, inlet, wing, and outlet. There you go. Okay. My bad. Yeah, if you have the name that matches, and then so like if I had already made these boundary conditions, and I had the same names as in the part, and then I assign the part to this region, then it'll automatically assign. But because I did it the other way around, it didn't. So let's go ahead. I'm just gonna create a plane so that we can like look at the mesh. New mesh displayer. Existing displayer, yeah. Okay. People on UW Formula Motorsport, if you have worked on the mesh, is this a good mesh? No? Okay, why?
It's very coarse.
Very coarse?
You're not really defining like multiple regions where you care about like the very far away parts, which you care about less. It's just as fine as like closer to the wing where there's going to be doing more interesting stuff.
Yeah. Yeah, and then I think another, kind of like you said, it's too coarse, and especially close to the wing. It's just way too coarse. So a couple ways we can fix that. Like mentioned, we want to do this smart. We want to make close to the wing more efficient. We don't want to make the whole thing be fine because that's inefficient. So how can we do that? We can do custom controls. So the first one is you want to do a surface control. We're going to apply that to the wing. So the first thing you're going to do once you do that, open up the controls. You're going to want to tell it, I'm going to want a different target surface size, and I'm going to want different prism layers. And the prism layers are like these two cells here, but basically this is just going to let you like refine the boundary layer. And if you remember the training from last week, you know what I'm talking about. You're going to basically want to change, we're going to change the number of layers, the total thickness, and the distribution. Change that to absolute. We're going to make this like 5 mm. Custom prism values, I don't know, 15. Change this to 1.2. 1.5 is kind of massive. This 1.5 values, it takes the thickness of the cell closer to the wall and multiplies its thickness by whatever scale you put. So we put 1.2. So it's going to take that thickness, multiply by 1.2, and that's the thickness of the new one. And then the total thickness, I don't know, like we're going to say 3 mm. Let's go ahead and remesh. Oh, and you know what I forgot to do? I forgot to make this parallel. Okay. Yeah, so while it's doing that, probably should have made this coarser. fine. It's a small sim. Okay, so we should see it update once it's done.
How small can your computer go for this type of size?
It's hard to like. I haven't really tried to go too far, but like it also depends on total cells. So it's like if I go super small, it's like gonna blow up in terms of cell count. So I haven't really tried. So here's kind of an issue that I've had to run into a couple times. Sometimes like it deletes the prism layer because it's like, oh no, it's too small. And so you have to change this number to like 0.01 and like 0. Yeah, it's stupid. We'll change this to a bigger number because I don't want to keep you guys here too long, so we're going to change this to 10. And then we're also going to add in a volumetric control. And to do that, we're going to create a new part of a block. I'm just kind of doing this by eye right now. Okay, go down to your volumetric control, block, trimmer, isotropic, absolute. Sure, that's fine. Make it 5. Oh, the internet's taking a crap. Okay. It's going a lot faster. Nice. Ah. Okay, there you go. And look at those nice prism layers. I probably made them too thin, but I guess we'll find out soon enough. So you can see that's my control that I put, and it tried to like make it a smooth transition somewhat. So let's go ahead and simulate this now. So we basically have the mesh, we have the physics, we have the region, we have all the parts. I guess it would be kind of cool to show you guys scalar and vector. Let's go ahead and basically what we're going to do is we're going to put the streamlines, if you want to call them that, onto that plane we put. We're going to change this to line integral convolution, velocity, yeah, that's fine. Okay, vector magnitude, okay, and run it. Wow. Wow. Yeah. Then you can hide this, or sorry, make another one. This time, this time we're going to put it on the wing. Shear stress. Shit, there you go. So you can see something somewhat weird is kind of going on right here. You're basically just taking the tangent of the velocity vector and just imposing it onto the surface. But you can see that like as it's converging, it like whatever was happening there is kind of like smoothing out, and that's probably just because like the whole domain is initially initialized as zero velocity everywhere, and so it just takes time to like refine that out. Can anyone guess what's happening here? Anyone on Discord? Does anyone on Discord want to guess what's happening on these on this right here? Like why is it going a like weird direction? Why is it like going at an angle? Anybody?
Is it because the flow is slipping to the outside of the wing?
It's what, sorry?
The flow is slipping to the outside of the wing?
Yeah. Do you know why it's doing that? It was something that we talked about in the training session last week.
I don't know, I always thought that was just always happening in airports. It's like, that's how the flow moves. So, I guess the pressure difference, the pressure gradient?
Yeah. Yeah, that's kind of like the root thing that's causing it. So, you go ahead and stop this. Oh, shit. There you go. Let's go ahead and do that. And we're going to do an existing display. We're going to put on the vector 1. And let's see if we can see them. Wow, it's the wingtip vortices. All right, let me hide that. You can see it's kind of like going from the pressure side. It takes a while to like render, or not render, but like, there you go. So it's like you see like the flow is going from the pressure side to the suction side. So that's the wingtip vortex. Or there's two of them. So you can see it's like, yeah, it looks like it's they're not even because this one is closer to the wall or the symmetry plane than this one. So I guess that's a cool visualization of what happens when you mess up your boundary conditions. If we wanted to get the force out of this, let me just reset the mesh, so reset the simulation. If we wanted to get the force, metrics, or sorry, flow energy, yeah. Force, I'm going to call this lift, aka, or downforce, whatever you want to call it, 0, 1, 0. And then we can also do drag. That is already in the X direction, so what we're going to do is we're going to take this, create a monitor and a plot in a single plot. So basically monitor plot, so monitor's now just going to have an output on this little output on the bottom, and then obviously the plot's going to plot it. So what we can do here is we can visualize the plot on one and the vector seen on another. And then let me go ahead and show this, hide this, and let's run it. Oh wait, shit. I forgot to Oh yeah, quick tip for reports, if you're going to do something that affects both of them at the same time, you can just multi-select like that. I just forgot to assign them to the wing. Okay, now they should, there you go. So yeah, you can see like the way it was initialized was kind of dumb. The best way to initialize it is inside of your initial conditions. You can just define the velocity as like already going at whatever velocity you want it to put at, and then it just has to refine the wake. So yeah, that's how you CAD, import, and simulate a wing. Any questions? No. Any questions on Discord? No? Okay, that means that I can theoretically expect you guys to recreate this for me if I asked you to. No, I'm not going to do that to you. But yeah, so there's other things you can do, like in the scalar scene here. If you want to see the pressure, you can do so. You can do P. Pressure on the wing. Suction, pressure, net force. Yeah. You could also theoretically use static pressure, but I'm pretty sure they're just going to be the same thing here. Yeah, same thing. So, and you can see like it converged. So like it's not even moving at this point. So yeah, we can stop the simulation here. We technically could have stopped it like, 230, whatever, but who cares? So yeah, if there's no questions, I guess I will leave you guys, but if there are questions, ask them now. Remember the lesson we learned about earlier today about speaking up. So, okay, thank you.